людьми.
Да, еще на моих компьютерах еще 6 минут имеется.
6 минут.
Да,
Ну, у нас ровно.
У нас ровно. Да, у нас...
давайте тогда, все, начинаем.
Okay, now we continue our Uzbekistan-Ukrainian lectures on the stochastic process. Today's speaker is Professor Bakoev with continuation of the talk on the numerical approximation of SDE in financial mathematics. Please, Professor Bakoev.
Good morning, dear colleagues. Let me continue my lecture. And if you allow to me to demonstrate the screen, I will start. Just a moment. Okay. Today I will last lecture was about application of the stochastic differential equation or stochastic process in finance, and I paid attention to the how we apply the stochastic differential equation in finance. Now after discussion some problems which was in previous lecture. Today I will give the lecture which I told simulation of diffusion process with R. Okay? Естественно, я хочу.
Да. Хорошо видно и хорошо слышно. Можете продолжать.
Okay, for this one, I prepared some lectures using R and R Markdown, which you can see the process of working with R and R Markdown. This is the R Studio, and this file is R Markdown, which is an interactive document. One of the plus of R Studio in order to prepare some material. That's why I use R Studio. And this I marked down the document. And now my talk about simulation of diffusion process. This is a package sim-diff-proc in R. This package provides uses a wide range of tools. They simulate, estimate, analyze, visualization, the dynamic of stochastic differential system in both form, Ethos and Stratanovich. And I will show for some examples in the further. And the next one is using this package, we can use the Monte Carlo methods for simulation or for the solution of stochastic differential equation, or maybe the and it is one more main subject is parallel Monte Carlo we can use in order to solve some economical or problem or financial problem using this package. There are a lot of functions. There's the following some of the functions of this package I can give. The first one, simulation of the 1, 2, and 3 dimension stochastic differential equation of Ethos or Stratanovich types with the difference methods. And the second one, simulation of the 1, 2, 3 dimension diffusion bridge of Ethos and Stratanovich with difference methods. Simulation, the first passage time, 1, 2, 3 dimensions, or calculate symbolic ordinary differential equation of the moment equation, means variance, covariance, etc. Monte Carlo replicate on statistic. Oh, you can use Monte Carlo methods in parallel or no parallel methods. Computing basic statistics, mean, variance, etc. of the process at time t using Monte Carlo methods. Random number generation, approximate of transaction density, approximate density of first passage time, computing Ethos and stochastic integrals, etc. And one thing is estimate drift and diffusion parameters of the stochastic differential equation or the stochastic process. Converting simulation diffusion SimDiffProp object to LaTeX, because you can convert some graphics or some tools to LaTeX too. Displaying the object class stochastic differential equation 1, 2, 3 dimension. And this is one main functions of this package. Is it clear? Яков Аке, естілепті ме? Нормально?
Да, нормально, все хорошо.
Okay. Okay, let's start. I will start with the simplest things, and then a little bit more step by step. I will go to the stochastic differential, general stochastic differential equation. And BM, Brown motion, Brown bridge, geometric Brown motion, and arithmetic Brown motion simulators. And these simulators, and you can find the function, for example, BM, this is a function about Brown motion. BB, function a simulator of Brown bridge. GBM, it is a generator for geometric Brown motion. And ABM, arithmetic Brown motion simulators. And for all of these functions, the arguments, and in the future we will denote by n. It is a number of simulator steps. It means if you give the steps, you can discretization with these n steps. M is the number of trajectory, or you can say it is the volume of the sample. X0, initial value of the process at time t0. Y, it is the terminal value of process at time t of the Brown bridge, because in Brown bridge you need now two values of the process and the beginning in the end. T0 is the initial time. This t is the final time. dt is a time step to simulate discretization. Usually we use this one in default. Discretization time is t minus t0 divided by number of steps. Theta is the interest rate it is a drift. Sigma volatility in the these processes. Let's in the future we will use these arguments this denotation. Let's start from the simplest one. BM, Brown motion, you know, it is a family for us. The function trajectory Brown motion use this equation, this differential equation, or you can say it is this one. In this case, here n01 is normal distribution. We use this function BM. It is a number of steps. This is the number of trajectory. Okay, we use only one sample. The initial value of the x initial time and the final time, dt null, it means the discretization time is this one here. After that, we have this, using this function, we receive this value. You know, it is x0 and etc. Until it was the step was 100, and we have 101 values of the Brown motion. And now, using this one, I can denote by Z the variable, this Brown motion. I can give the plot of this Brown motion, this one. This function using plot. This is a Brown motion with one trajectory of Brown motion. And in order to understand, we can use this process and give some function of this process. I'll give here, I choose 10 trajectory here. This is a 10. And this red one is the mean value of this trajectory in each time, this red one. If I put here any number, you can find, you can draw, you can simulate this Brown motion and find this function too. Is it clear? This is a function Brown motion. This is a plot. This is the plot of the X and plot of the mean, row mean. May I continue?
Okay.
Okay. And next one, Brownian bridge. What's the Brownian bridge? The function BB returns the trajectory of Brownian bridge starting at x0 at time t0 and ending at y at time t. The diffusion process, the solution of the next stochastic differential equation. Okay. This is a stochastic differential equation with according to Brownian bridge. And this function BB, Brownian bridge, this is number of steps. This is number of trajectory. This is the value of x at time t0. The y, the value of y at t equal 1, etc. This function, and the simulation of the one sample. This one. This function gives to us this sample. And that one, this is the variable I give this one sample. If you put here, you can see the plot of this Brown bridge. And here I have 100 sample, not 10, 100 sample. And the red one is the mean value of these samples at each time. And black one is the simulation of the bridge, Brown bridge. Okay. The next one, geometric Brown motion. The GBM function returns the trajectory of the geometric Brown motion starting at x0 at time t0, and the diffusion process is the solution of the next stochastic differential equation. Please pay attention for this geometric Brown motion. You know, in the previous lecture, I'll give that the model of Black shows a lot of models of in finance, in option pricing, use this geometric Brown motion. For this one, this function, this is a number of steps. Yeah. Number of trajectory, initial value, and final time, and theta equal 1 and sigma equal 1 in this case. I can change, but in this case, it is the same. I choose these parameters, drift and volatility is equal 1. For this one, we have this sample, which is a geometric Brown motion. Okay, and the same procedure for this is the variables for geometric Brown motion, and this is a plot of the geometric bridge motion. I have 100 sample as the volume of sample 100. In this case, it is a Brown motion, a geometric Brown motion. As the red one is mean value. Okay. The next one, arithmetic Brown motion. The function ABM returns the trajectory of arithmetic Brown motion starting at x0 at time t0, and the diffusion process solution of the next stochastic differential equation, this one. The function ABM with these parameters, this is a number of steps, 100, number of sample, x0, t0, t, and the steps of in iteration, theta equals 0, sigma equal 1. Okay. This is a sample, the same procedure. I put here this variable and the plot, and the mean row means is here, this one, this arithmetic, and this. Okay, may I continue? Okay, нормально, okay. And the next one, the next process is in some textbook you can find this Hull-White or Weissenschick process, HWV. This function returns the trajectory of Hull-White, this process starting at x0 at time t0, and the diffusion process solution of this, the next stochastic differential equation, this one. Here is mu and theta and sigma, the parameters of this stochastic differential equation. Now here I see the x is this Hull-White process with n equal 100. It's the steps. It's the volume of sample, and mu equal 4, theta equals this, sigma this one, and you can x0 is 10. In this case, you can see this is the the plot of this stochastic process. Okay. And the next one, Ornstein-Uhlenbeck process. You know, it is a more famous process which we use in finance, in financial management. That's why I took this process too, in order to show how we can simulate or how we can solve this stochastic differential equation using the function OU or U. And the diffusion process solution of stochastic differential equation of this one. Here mu and sigma is the parameters of this process, parameters of this model. And you can see it's the number of trajectories, this one, and mu is here. And you can plot this process here, the same. It's the red one is mean value and black one is the sample. Okay, is it clear? If you have some question, please. If you have no question, I will continue. Okay, Yakovaka, may I continue?
Вопроса нету, пока вопросов нет.
Okay, let's continue. Now I will go simulation of one-dimensional stochastic differential equation using R. And okay, question? No. Okay, let's this we call this function S, and this is the name of function for simulation. And let's we analyze or we discuss or consider the next stochastic Ethos stochastic differential equation, this, or Stratanovich stochastic differential equation of this. Here is this R is some function. We will A and B must be satisfies the condition of the unique of the existing of the solution of this differential equation. But I will not pay attention for this A, B. Now I will give the ways of simulating of this solution of this differential equation. And the same here. In this package, this package used a lot of methods for simulation. The simplest one is Euler-Maruyama order 0.5. This is the order of convergence is this one, and we can use the Milstein method with order 1, Milstein method with order 2, or you can use another method for simulating or for solution of the stochastic differential equation. It is a Ito-Taylor method with order 1.5, or Runge-Kutta methods for the order 1, 2, 3, etc. But we can use any of these methods in order to simulate the solution of the stochastic differential equation type of Ethos or Stratanovich. Here is what does it mean? It's this function returns the trajectory of the solution of this stochastic differential equation. Here is x is the trajectory, drift coefficient, diffusion coefficient, and type of the solution. You can show the type of the solution. Let's consider some examples. Here, one example. For example, here, this f is a 2 multiply 3 minus x. It's the drift. This one, this drift. Here is this, and this diffusion coefficient is this one. Diffusion coefficient, and then mod, it means I give drift equal f, diffusion equal g, and the volume of m equal 400, x0 10, and dt with this step. The mod 1, it is the statistical characteristics of the solution of this equation here. Initial value summary is here, gives a summary. Just a moment. Mod 1, in mod 1, the mean value, variance, median, mode, first quarter, etc., etc. The summary of xt is here. And in this case, we analyze the solution of the stochastic differential equation as a time series with this date. This is a summary. Which we have here? The mean value, variance, median, mode, first quartile, third quartile, minimum, maximum, etc. Coefficient of variation. Yeah. This is a plot of this solution of stochastic differential equation. Look here, this is the black one is a sample. Sample volume of the 400, I think, there, yeah. Oh, and red one is the mean value, or mean, yes, mean value of this sample, and blue one is the confidence interval for lower confidence interval and upper confidence interval for this the solution of this stochastic differential equation. Okay. And the next one, the next example, it was the Ethos stochastic differential equation. The next example about the Stratanovich stochastic differential equation. With this Stratanovich differential equation, we can use the function. This is a drift. 2 minus x divide 2 minus t, and this is a diffusion coefficient, and the mod, it means what type of STR, it means Stratanovich differential equation with drift f and diffusion q. The volume of the sample is 400, and with this data methods we used Milstein with order 1. In this case, we have the next summary statistics for this one. The mean value, etc. The statistics. Okay. This is a plot. Oh, just a minute. The same. The black one is sample, or yes, sample, and a red one is the mean, and blue one is the confidence interval for the mean value of this trajectory of the process. Okay. Hey, I continue.
Yes.
Okay, the next one. Okay, simulation of two-dimensional stochastic differential equations. And we consider the two-dimensional stochastic differential equation of the type of Ethos to the two-dimensional stochastic differential equation. Ethos look like this X and Y. And two-dimensional Stratanovich stochastic differential equation is like this. And in this case, we can discuss, or we can simulate two types of the solutions. The first one, we can say this omega-1 and omega-2 are two standard Brown motion with independent. It is a correlation between this equals 0. And then we can discuss this when we have some correlation between omega-1 and omega-2 with the correlation matrix. Here, for the system of the stochastic differential equation, you can use the same a lot of the methods, the following methods. It's the Euler. Just a minute. Sorry. You can use Euler methods, Milstein methods, or Runge-Kute methods, etc., etc. It depends what kind of the order of convergency you want. If you want 0.5, it is easy to use Euler-Mariam Euler methods. If you want to more exactly work, and you can use Milstein or you can use Runge-Kute method, but in this case you can lose by simulation time, maybe efficiency of the simulating, maybe it's different. Okay, as an example, let's analyze, we consider these two equations, the system of this stochastic differential equation with this functions. Look here, this one, it's A, this is the sigma 1, this is A2, and sigma 2. And now in this case, you can write as a function is a, or parameters or function is a as a vector. Look here, this is a A, this is a B, A for the second one. This is a vector. And the same for diffusion coefficient, the same. This is 1 and 2 as a vector. And if you say mod, this is a with drift fx, diffusion gx, and the number of trajectories 100, you can see. And mod 2d1 is this one. This is summary statistics for this process X and Y, But we can we can find the all value of X and Y, but it's not interesting for us because it takes a lot of places. That's why I'll give only summary statistics for these two, the solution of these two stochastic differential equations or system of stochastic differential equations. Okay. And the next one is, the next example is about a solution of the system of stochastic differential equation, Stratanovich stochastic differential equation. And the same procedure, and you can write this one, or only you have to put here, this is the type of equation here, STR. And then you can solve this system of stochastic differential equation type of Stratanovich. Methods we used Euler, and we have the result, summary result. You can see, you can find it's like this one. And the next one, the same procedure, we have simulation of 3D stochastic differential equation. Okay, system of 3D stochastic differential with 3 equations. This is a 3D Ethos stochastic differential equation here. This as a 3-dimension Stratanovich stochastic differential equation with this standard where W1 and 2 and 3 standard Brown motion independent. It doesn't matter, you can use independent and you can use with some correlation matrix. We have a procedure using this with correlation matrix too. Example. This is the summary statistics for the solution of this 3-dimensional stochastic differential equation system. It was for the Ethos, the next one for the Stratanovich. You can use this one too. Okay. And now in my lecture, I showed you some function for stochastic simulation, stochastic diffusion process. If you allow to me, I will show some examples and I will show the packages in R. May I continue?
Yes, you can.
Okay. You know, this is the R Studio. In R Studio, we have here packages. In packages, we have this simulation diffusion process. I'll give some examples from these packages, but you can use, we have a lot of function, and if you go here and you can see this is the functions. We discuss only some of these functions. We discuss BM, we discuss bridge, or we don't discuss bridge for stochastic differential equation, etc., etc. This all functions here. And using this package, you can simulate or you can estimate the option price, or you can use this stochastic differential equation in order to solve some physical problem or financial problem or economic problems. but it is very good and very suitable package. This package, look, you can find a lot of package for stochastic modeling in R. Nowadays, you know, R is one of the more popular software, and using this, you can do a lot of. I have some examples here for, in order to show to you how to, just a moment, I can run it. Yeah, of course. Here, this is a plot of two-dimensional, the solution of two-dimensional Ethos stochastic differential equation. So I have somewhere three-dimensional too. Oh, sorry. Okay, here you can find three-dimensional graph. Okay, and the next is very useful. The function of the RStudio is you can prepare your some article or some topic, some lecture using R Markdown or R Markbook. It is easy. You can prepare the file, HTML file, Word file, and PDF files using this R Markdown. Oh, it's some of the picture he draw using this model. And if you use R Markdown, for example, this R Markdown here, I put here something like this, and you can check here the solution of all of this. Look here, this one. Okay, it was, I finished my lecture. If you have questions, some question, I am ready to answer.
Thank you very much for interesting talk. And maybe somebody have questions, comments, please.
I have a question.
Okay, please.
Can we calculate or find limit superior line of this kind of differential equations? I mean, limit superior line is some only finite number of simulations over that line, like the law of iterated logarithm.
Mm-hmm. Okay. Yes, of course. I'll show to you how we can simulate the trajectory of the stochastic differential equation or stochastic processes. If you write some function or functional from the trajectory of this process, you can calculate any function or functionals for calculating. It's a mathematical expectation of the some function from the trajectory give to you a solution of your problem. It means only you have to put the right equation. You have to write equation, and you have to write the function which will be estimation of the solution of your problem. Okay. But it depends the covariant скоросходимости. It means the
rate of convergence.
The rates of converting, yeah, or it means if you give some which variant or which standard deviation or which error do you want, looking at the error, you can manage your estimator.
Okay, thank you.
Okay, thank you. Other questions, please?
I have another question.
Mhm.
What about inverse problem? I mean, if they're given some trend like time series, and can we find approximately differential equation of it?
Yes, of course, a good question. If you look at this, just a minute, that is packages, the simulation process, we have here a lot of function, and we have a function for the solution of inverse problem too. In order to, you have to look through all this function for this package, and we have another package they call CDS, Stochastic Differential Equation, CDE, and using these packages you can simulate or you can solve inverse problem too. I think we have some here this function for inverse problem. But all of this in numerical, not analytical solution, not analytical, but numerical.
Thank you. Other questions, please? I also have question. You described procedures based on the Milstein or Euler-Maruyama regime, and does your calculation depend on the degeneracy of the coefficients? For example, if coefficients became to be equal to 0 on the sum line in two-dimensional case, how fast calculations will be near this line or something?
Yes, I understand. Okay, a good question, because you know, I said is in my task usually I have assumption that this stochastic system of stochastic differential equation exists the solution and unit solution if the coefficient satisfies these conditions. I will simulate, because I don't research about behavior of the coefficient, because in my task I solve the financial problems. In financial problems, usually the coefficients satisfy all conditions for existence of the solution.
Okay, I see. But it seems to me that it will be very interesting to apply this numerical methods to epidemic discussions, because now a lot of diffusion models exist in epidemiology, and most of them is based on the degenerated equations, and actually we want to estimate the moment of the first hitting of the zero. So maybe it will be interesting to see such applications too.
Yeah, because you know, in the beginning of the COVID-19, with some students, we began to work with this model, epidemiologic models. But nowadays we have some results, but it's not so good for us. But we are looking for this. We use deterministic models, but I said it will be better if we use a stochastic model. Yes, actually.
You know, I have some young colleague, Jigran Jai, from London Queen Mary University. She did her PhD thesis with my help, and she provided such a diffusion model where the most interesting was the estimation of the distribution of the first heating time for the generated equation. So I will contact her and ask her to send to you her papers. Maybe it will be interesting to see, and maybe some numerical analysis will be very interesting in this case.
Okay, good, wonderful. Yes, it will. If it will be good if we make some joint research with modeling
Yeah,
process.
yeah, I think it will be interesting.
Yeah.
Okay, thank you very much. Some other questions or comments, please? Okay, if there are no other questions, then thank you, speaker. Thank to speaker again. And our next session will be after a week with the lectures of Professor Portenko. Thanks everybody, and bye.